Hello everyone, I hope that you're great. Now I'm going to do a little run through some chemistry topic. Well, we can call this a crash course, but unfortunately, it is not everything that I want to do. Chemistry is wide and especially a lot of drawings and formulas and all of that stuff. All right, so I'm just presenting a few topics. Well, it'll be a lot of topics because it's really long, but it's not the complete thing. All right, I mean, I'll upgrade this in the coming year. All right, so as you know that the chemistry course is divided into three sections. You have the principles of chemistry, you have organic chemistry, and you have inorganic chemistry. All right, so the first thing, however, is to just kind of do a quick recap on graphs because it is similar across the sciences, and so it is good for you to know how to draw a graph and label a graph. And so what you need to know is that a graph shows the relationship between variables, and persons who have watched the bio crash course would have already been through this. All right, so I'm going to quickly go through it. And again, we have two variables that we put on a graph. We have the independent variable that goes on the x-axis. All right, and again, what we need to know about the independent variable is that during an experiment, it is that variable that you, the experimenter, have changed. Okay, so in other words, you manipulate that variable. And the reason why you manipulate that variable is to see how it will change other variable or variables. All right, and so therefore the last point is that an independent variable causes another variable to change. All right, so for example, time and temperature. All right, so these things will change other variables. And those other variables, we call them dependent variables. And dependent variables are placed on the y-axis. All right, and again, the dependent variable change based on the changes in the independent variable. So for example, rate of photosynthesis, growth, water loss, the production of certain gases, and so on. All right. And so a typical example that you might see as a graph is time and volume of gas produced. And this will be for a rate of reaction experiment where you're producing gas in a certain amount of time. So typically you could be reacting an acid with a carbonate. All right. And so again, these are just made up numbers. All right, just for your understanding purpose. And again, just to show you the graph and then show you the data. So from the data, we have a graph looking like this. Again, time will be placed on the x-axis because time is independent and volume of gas produced is dependent. So as the time is progressing, then the volume of gas may increase or decrease. All right. So time affects the gas, but the gas does not affect the time. All right, and hence the graph will look something like that. Now, the most important thing you also need to know as well, beside plotting the graph, is that you should give a graph a title. If you should draw a graph, you should also label the axis properly with the units as well. And you should use fine points for your coordinates and also smooth lines for the graph itself, or the plot in the graph. All right. All right. So bear that in mind. All right. Now let's run through some basic chemistry. And again, these are just principles for your understanding, especially for those I know some of you might be missing classes, or you may not have a teacher for a period of time, as some of you mentioned. And of course, I couldn't sleep without going through this. All right. And so we need to know the difference between atom, element, and compound. All right. And so, in a brief way, we have atom. An atom is simply the smallest particle of matter or anything that exists. And then we have element. An element contains the same type of atoms. All right. And that's why we normally interchange the word atom for elements, because they pretty much are the same thing in terms of properties. All right. Because an element consists of the same type of atom. All right. And so a compound is any substance that contains atoms of two or more different elements. So what is important here? A compound must at least has two or more different elements chemically combined. So the key word here is different. So for example, if you notice carbon and oxygen joined together, they're different elements. All right. And so that is a compound. All right, so that's very important. It cannot be the same element. It's not a compound. I will talk about that shortly. All right, so again, as we know about atoms, very important thing we need to know about atom is that atom have different parts. So we have the nucleus, which is the central part, containing the proton and neutron. So P is for proton, N is for neutron. All right. And also around the nucleus, what we have is a shell or shells, depending on the number of shells. And the shells will contain electrons. All right. So electrons are on the shells. And so those are basic things that you need to know. All right. Now, what you also need to know about these particles that are in atoms, we call them subatomic particles. And these subatomic particles are located in different parts. They have different charges and different mass. So, for example, electron, those can be found on the shells, all right, or shell depending if it has only one shell. The charge of an electron is negative. It has a mass of 0, technically speaking, all right. And proton is found in the nucleus. All right, so a proton is found in the nucleus, or protons are found in the nucleus. And then protons have positive charge, all right, and a mass of 1, a relative mass, matter of fact. All right, this is not the true mass. All right, and neutrons now, they are found in the nucleus as well, just as proton. No charge, but a mass of 1. And so by this, you should realize that the total mass of an atom is based upon the proton and neutrons, because protons and neutrons are the only particles, subatomic particles that have mass. All right, so the electron is not contributing to the mass. But for the overall charge of the atom, which is 0, we have electron, which is negative, and protons, which are positive. And we have equal number of protons and electrons, and so therefore the overall charge of a naturally occurring atom is 0. All right, the nucleus is positively charged, all right, because the protons are there in the nucleus. All right. Now again, we say nucleus contains protons and neutrons. All right, and so therefore they contribute to the overall charge of a positive charge. 0 plus positive is a positive. All right, the total mass of an atom is based on the proton and the neutron, because those are the two particles that have masses. All right, electrons, 0 mass. All right, now an element, as I said, an element contains the same type of atoms. And so therefore, elements, for example, if you look at the periodic table, you see elements, all right? So when you look at the periodic table, you see elements. And so a quick kind of thing to kind of distinguish between elements and atoms. If you think about atoms, you have to draw the rings, okay? You have to draw the rings. And when you draw elements now, you only write the symbol, really. All right, so for example, carbon is a very popular element that we need to know. And you notice that there are two numbers here. We have the larger number, all right, and we have the smaller number. So the larger number is the mass, the smaller number is the proton number, all right, and the proton number is the same thing as the atomic number. And of course, the C, it is a symbol of the element. Carbon is the name, all right, so those are basic things that you should know. All right, I'm just going through this because most of you should know this already, all right. Another example here is sodium, all right. And compounds now is, again, as we mentioned earlier, that compounds contain different elements combined. All right. And so again, for carbon dioxide, you have carbon and oxygen. All right. So those are two different elements there. All right. And the number that you'll see in the formula of a compound represent the number of atoms. All right, or the number of each atom. All right. And so again, we have two elements two elements make up this compound, carbon and oxygen. But however, there are 3 atoms, 1 atom of carbon and 3 atoms of oxygen. All right, and 2 atoms of oxygen, which gives a total of 3. All right, so 1 plus 2 is 3. All right, sodium carbonate, for example, is another compound right here containing sodium, carbon, and oxygen. And for this, the number of elements, we have 3 elements here: sodium, carbon, oxygen. And we also have a total here of 6 atoms. How we know is 6? We have 2 sodium atoms, we have 1 carbon atom, and we have 3 atoms of oxygen. And so a total of 6 atoms, but only 3 elements. All right, so those are basic things you should know. And those are really for multiple choice type of thing. All right, and so again, 3 elements, 6 atoms. All right, so again, we have sodium carbonate versus oxygen right here. And this, we're going to use these 2 examples to discuss the difference between a compound and a molecule. So looking at compounds now and molecules, what's the difference? All right, and I guess some people have been mixing up molecules with compound, but I will tell you this quickly, that all compounds are molecules, but not all molecules are compound. All right, and so let us go into it real quickly. And so this you should make a wild guess. As you know, you can just pause and do that quickly. Which one is a compound, which one is a molecule. But of course, I'm not going to waste time. I have far to go in this. All right, and so quickly, the difference between a compound and a molecule is that a compound contains atoms of two or more different elements chemically combined. However, now a molecule contains atoms of two or more elements. They can be the same or different. All right, and they are chemically combined. So they are similar in the sense that they are chemically combined. The atoms or elements in molecules can be the same or different. But in a compound, the elements or atoms must be different. All right, and that's the difference between compound and molecule. All right. And so by nature of this, we should know these, which is the molecule is a compound. I'm going to go through this fast. And so the first one, it can be either a molecule or a compound. All right. The elements are different, and all compounds, again, as I mentioned, they are molecules, but not all molecules are compound. So oxygen, for example, diatomic oxygen is a molecule, not a compound, because you only have one type of element, all right, or one type of atom. Nitrogen gas as well is a molecule, not a compound. Carbon dioxide is a compound and also a molecule. Water, which is H2, is a compound or molecule as well. All right. Now, as I mentioned earlier, that all compounds are molecules, but not all molecules are compound. All right. That's very important for us to know. All right. And now we'll look at these substances as example. All right. We're going to talk about if they're atoms, molecules, or compound. Again, let's just do this quickly. No time to waste. Atoms that are present in sodium chloride is sodium and chlorine, so therefore it is a molecule, and therefore is also a compound because they're different. Cl contain only Cl. Cl2 only contains Cl, I should say, and so therefore it is a molecule but not a compound because it only has one type of elements or atoms. Cl by itself only have an atom of Cl, and so therefore it's not a molecule, all right, because it's only one single thing, and so it's neither a compound as well. It's really represent what they call the element, all right? All right, so metals versus non-metals now, real quick. And this is something that you need to know. All right, again, we're just trying to rush through this as fast as we possibly can. All right, and so pretty much what do you need to know about metals and non-metals, right? Is simply you need to know the atomic number of all the elements, well, first 20 elements for CSEC, all right? And if you're watching for BGCSE as well, it is only the first 20 elements you should know from the back of your hand, all right? All right, so we know the atomic number, and we also need to know electron or electronic configuration. And so we need to know to do that. And so again, the first shell always hold a maximum of 2 electrons, the others maximum of 8. And you must fill the first shell first before you go on to the second, third, or fourth, if they exist. All right. And so if I have 7 electrons, for example, 2 will be in the first shell, and the next 5 could hold on the second shell because the second shell holds a maximum of 8. All right. So therefore, it's 2, 5. Now, the idea of getting this is that the valence electrons tells us what type of element is it, whether a metal or non-metal, right? All right, so the valency tells us what group it is in as well, very important. And the valency or the valence shell electrons or the valence electrons, which are the electrons on the very last shell, tells us a lot about the element, all right, or atom. All right, so metals now, they have 1, 2, or 3 valence electrons, while non-metals now, they only have 5, 6, or 7 valence electrons. Now you may ask a question, what about those with 4 valence electrons? Some of those are called metalloids, so we don't really classify them as distinct metals or non-metals, right? Or just non-metals purely. Majority of them though will be non-metals. Popular one is carbon, all right? But we talk about that later when we talk about carbon compounds. All right, so for example, here we have magnesium, all right? And magnesium has 12 electrons, 2, 8, and 2 on the last shell, so therefore is a metal. And we have here sulfur, and sulfur has 16 electrons, and so we have 2, 8, and 6, and so we have 6 valence electrons. Those are in red, so it makes it a non-metal, all right? Now, sodium and phosphorus, again, let's just distinguish between them. We have metal here for sodium because it has 1 valence electron. Phosphorus has 5, so it's a non-metal there, all right? Now we have these two, chlorine and helium, and chlorine has 7 valence electrons, so therefore it is a non-metal. All right, anything with 5, 6, or 7 again is non-metal. Now helium is special because it has a full first shell, and if it once the shell, whether the first or second or third, once the shell is filled, it is a noble gas or inert gas. All right, so it's neither metal or non-metal. So this is classified as a inert or noble gas. All right, just to mention that. And remember, they do not bond. So when you talk about bonding shortly, you'll realize that these do not bond. No, inert gases do not bond. All right, getting to know about the periodic table and how to identify which groups are metals and which groups are non-metals. And a quick thing to tell you that all the metals fall in the first 3 columns. And so starting from where you see lithium all the way over to boron, all right, they are metals. And if you look closely, you see the Roman numeral on top, 1, 2, and 3. All right, so the numbers tell you what group they are. So we have group 1 with only 1 valence electron. Group 2, they have 2 valence electrons. Group 3, they have 3 valence electrons. All right, and so those are all metals. The indentation right here, those are called the transition metals. All right, non-metals normally form from 5, 6, and 7. Again, some of the group 4 are also non-metals as well. Some are called metalloids, which show properties or characteristics of both metals and non-metals. All right. So again, now properties of metals and non-metals, that metals are tend to be shiny, as we all know that. Non-metals are tend to be dull. Metals are harder than non-metals for sure, while non-metals are brittle. Metals are malleable and ductile. Malleable mean it can be beaten into shape. Ductile means it could be pulled in the form of wire. All right, so malleability means it could be beaten into shape, and ductility means that it could be drawn into wire. So it's malleable and ductile. And the opposite is true for non-metals. They are non-malleable and also non-ductile. All right, and metals are good conductors. All right, good conductors of heat and electricity. All right, and non-metals are poor conductors of the same heat and electricity. Metals tend to be solid. Most of them are. We do have liquid metals, all right, but generally speaking, most metals are solid, and non-metals now tend to be either solid, liquid, or gas. All right. All right, now talk about forming ions. All right, and we're going to talk about forming monatomic ions first, then we can talk about diatomic ions later on. But the basic thing about forming ions that you need to know, all right, is that we're going to look at the valence electrons to determine whether or not you can form an ion. All right, and so again, we know that protons equal to the number of electrons with the same as atomic number. That's something else. That's a reminder, real quick. All right, so you can know the number of electrons based upon the number of protons. You can look at the periodic table for that. All right, and also you need to know that atoms are electrically neutral, which means no charge, because you have equal electrons with equal what? Protons. So by existing as in a natural state or the elementary state, atoms are neutrally charged. But how do they become charged? Very important. All right, so one of these particles, whether proton or electron, must be different. But which one is actually different? And we're going to learn that right now. Now, the thing is that, again, ions are charged particles. Very important to know that. And so how you become charged, for example, sodium plus, how it became that. And simply because, remember, originally, same proton, same electron. So it happens that the protons remain in the nucleus, but the electrons can be either gained or lost. And that's the difference between charged and uncharged particles, all right? So it's the difference between electrons. The protons remain the same. All right, so now let's talk about that now. Again, as I just mentioned, that ions are formed when atoms lose or gain what? Valence electrons. Not just any electrons, but the valence one, the ones on the last shell. Those that are the ones that can be easily lost or gained. All right. And so, again, metal versus non-metal. Again, metals, they lose valence electrons, so easier to lose electrons from metals, and it's easier to gain electrons for non-metals, all right? And that has to be what we call electronegativity properties. All right, we can discuss that later, all right? Again, and just to even mention electronegativity, because electronegativity is the ability for that element or atom to draw electrons towards it. So non-metals are more electronegative than metals. So non-metals are able to draw electrons closer to them. All right, compared to the metals itself. All right. All right. Again, metals become positively charged because they will give up their negative electrons, and non-metals now become negatively charged because they gain more negative electrons. All right. All right. And when metals form ions, we call them cations, and when non-metals form ions, we call them anions. All right. Now this is an example here of sodium. So sodium originally is 281, one valence electron. If it loses that one electron, what happens? It becomes 2 and 8. And so therefore now, if you think about the original one before it loses that one electron, we have 11 protons, 11 electrons. So therefore 11 positive plus 11 negative gives 0. However, when it lost that one electron, there are still 11 protons because the protons remain unchanged. Once the proton change, is no longer the same element, okay? Because that's what determines the characteristic of an element or atom is a number of what? Protons. And so in this case now we only have 2 plus 8, which is 10 electrons. So 10 plus 11, we get a positive 1. So sodium is positive 1 in this case, all right? And that's why sodium is Na+, all right? So that's just a basic revision of how you form ions. So let's do -1, oxygen, for example. There are 6 valence electrons. So electron configuration here is 2, 6. Again, here what's going to happen is a non-metal, so we're going to gain electron to fill that shell. So to fill that shell, which is the second shell, you need 2 more to become 8, so it becomes 2 and 8, okay? So originally, for oxygen, before it gained those 2 electrons, it was 8 and 8. 8 protons, 8 electrons, all right? And so therefore, the total charge here was 0. However, now it gained 2 more electrons, which become 10 electrons instead of 8, but we still have 8 protons, 8 positive plus 8 plus 10 negative actually. What we get here is -2. So therefore, oxygen becomes O2 minus. All right? All right. Now, one more example here. I think I have more examples, but I'm going to skip over them in the interest of time. Aluminum, for example, has 3 valence electrons. Again, 2 and 8 because it lost those 3 electrons. Metals lose electrons originally, 13 and 13, 0 charge. And now if it lost those 3 electrons, it becomes 13 and 10. And so 13 plus -10 actually equals to +3. And so therefore, aluminum, for example, is 3 plus as an ion. All right. I'm going to skip through this one quickly. It's chlorine. All right. You can just look as you see the information present itself, and you can actually, if you want to pause, then it's up to you and look at the information. It's similar thing. No time to waste tonight. Definitely, I want to get some information in. All right. So again, just to make a note that easy way to identify the charge of any element, you can look at the group. For example, group 1, they are metals, they lose 1 electron and become +1. Group 2, they lose 2 electrons and become +2. Group 3, they lose 3 electrons and become +3. So everything in group 3 will be +3. Even the elements that you don't know, they are +3. All right. Now for group 5, they gain 3 electrons. Think about the word 5 to become 8. You need 3 more to become 8. So they gain 3 electrons, become -3. Group 6, there are 6 valence electrons, gain 2 more, and they become -2. And group 7 will gain only 1 electron to become 8, and they become -1. So you can know the charge of these elements by simply know what group they are in. All right? Simple thing. There's nothing to it. All right, the summary, just let's go through this quick. Ions are formed when atoms lose or gain electrons. All right, just quick. Metals form positive charge ions. We call them cations, just remember that. Non-metals form negatively charged ions, and we call those anions. All right? All right, so running through quickly. Again, electrons configuration of ions resemble that of the closest noble gas. So once you either gain or lose electrons, the last shell of that atom look like the closest noble gas to it, which means we call that the octet rule, all right? A fulfilled valence shell. All right, ionic bonding now, all right? And so this again, we're going to run through quickly. Well, everything we have to run through quickly because of interest of time. So ionic bonding is simple bonding involves the valence electrons of atoms. However, what ionic bonding is is the transfer of electrons from a metal to a non-metal. Just to make mention of that, right? So the transfer of electrons from a metal to a non-metal. That's very important. And we know metals, we know non-metals now. So for example, magnesium and sodium. All right, again, I'm only showing the full thing, but truthfully, you don't need to draw the inner shell electrons. There is no need. Those will help you to be confused if you draw them. You don't need to draw them. All right, so point to note here is that, for example, magnesium, it is a metal. It has 2 valence electrons. Sulfur, on the right, it has 6 valence electrons. Again, it's a non-metal. And an ionic bond must be between a metal and a non-metal. All right, or you can say a cation and an anion. All right. So again, there's no need to draw all the shells again when you're doing these things. So basic information about the definition for ionic bonding is a transfer of electrons between metals and non-metals. Electrons move from the metals to the non-metals. Again, metals lose, non-metals gain. So again, back to our example, electron configuration for sodium is 281. Electron configuration for chlorine is 287. All right, so again, we're only concerned about the valence electron or the valence electrons. So sodium will transfer its 1 valence electron to chlorine, like that. All right, and therefore it only requires 1 sodium to fulfill the need of chlorine gaining electrons. All right, so chlorine becomes 8, and sodium will lose at 1 electron as well. And so therefore what happened as a result, what we have here is 2,8 as the new electron configuration for the ion. So the electron configuration for the atom is different from the ion. I want you to know that. All right, so the element is different from the ion. All right, and so the formula for this will be NaCl, which is sodium chloride. Notice I had IDE at the end. Sodium, you write the full name of the metal, the stem name of the non-metal, and add IDE. All right, and that's why it becomes sodium chloride. All right, and next example here is sodium and oxygen. I'm going to do this. I have one more after this, but again, I just want to present it and you'll look at it on your own timing. Now, sodium, for example, again, going to bond with oxygen. In this case, again, we're only concerned about the valence electron. Notice that 1 valence electron goes over to oxygen, but oxygen is now 7. It still requires 1 more, okay, to become full. But the sodium already gave up that 1. Again, what is giving the electrons in this case is sodium. So what you have to do is to draw another sodium to give more electron. And so therefore, that electron will go over to make it now fully 8. And so therefore, to fulfill this type of requirement for this bond, or for all the elements to have their full valence shell electron, then we require 2 sodium, that's why it becomes Na2, and 1 oxygen, and so it's Na2O. All right, and that is sodium oxide. Again, all the ionic compounds end with IDE. All right. Now, calcium and chlorine, again, I'm just going to present information and just look at it. You notice the electrons are being transferred. All right. And again, in this case, we draw 2 chlorine because it requires 2 of them to receive those 2 electrons from the original calcium. All right. There's another one here. I'm not going to waste time with it again. This is my favorite, however. And even so, I'm not going to waste time with it. I'm going to present the information real quick so you can just watch and observe. All right, the electron is being transferred over to oxygen. Oxygen cannot take on any more, so you require more oxygen to receive the extra electrons. Electrons are being transferred real quick over. And then again, we have to keep on drawing until the receiving element and the giving elements, they give as much as they can and receive as much as they can. And then you will write your formula. So this is aluminum oxide. All right. All right. Now, ionic bonding again using the ions, which is the cations and anions. Those are we call them ions generally, cations and anions. And just to make a quick notation that we can separate these ions in terms of monatomic ions and polyatomic ions. Monatomic ions, those are thus the ions with only 1 element. And the polyatomic ions, those are the ones with more than 1 element in that ion. And so quickly share right here that monatomic ion, again, 1 atom is present. For example, sodium plus, Al3 plus, and O2 minus. Those are monatomic ions. Now, polyatomic ions, again, they contain more than 1 atoms or elements. For example, NH4 plus, which is ammonium ion, PO4 3 which is a phosphate ion, SO4, which is a sulfate ion, SO4 2 a matter of fact, which is a sulfate ion, All right, so those are just typical examples there. All right, however, now when ions are joined together, the overall charge should be 0 because compounds, they have 0 charge, all right? Just to make mention of that. Or once a molecule is formed, the overall charge is 0. All right, so now for example here now, we have sodium and the sodium ion and this chloride ion going to come together. If it does add them together, +1 and -1, that's already 0. So therefore we won't have NaCl. There's nothing to work out. All right. Next example, if you have sodium ion and oxygen ion, there if you add 1 to -2, then you're going to get a -1. So to combat that, what you're going to do is a crisscross. All right, so we're going to crisscross them and just drop those charges, like somebody say crisscross applesauce, drop it like it's hot, you see? Yeah, so you're going to just cross them over, all right? Crisscross them over like that. And then we're going to just drop those charges as actual numbers, all right? And so what you're going to get here, as a result, we have Na2 and sodium, Na2O, which is sodium oxide, all right? So we need 1 oxygen with 2 sodium to form that molecule, all right? Which is also a compound. All right, in this case, we have here hydrogen peroxide, all right? So this is a peroxide ion right here, which is O2 2 minus, and we have a +1. And so how to work this out now? Again, we're going to crisscross the charges. All right, the +1 will go over and -2 will go over. So drop those numbers down. And then what we're going to do is to work out our thing right there. So we're going to have 2 H's and O2. That is now hydrogen peroxide. All right. Again, the same thing here. We have 2 positive and 3 negative. Again, just crisscross them over, drop them down, and then we're going to work out our values. All right, and see how much we get there. All right. These in registry that the numbers are now equal. If you drop those numbers down and multiply the charge by them, that's what I should have to actually show you. But no time to go through all that full details. But you see what I'm doing here. Just drop the numbers down. But notice we have a polyatomic ion right here. And this 2 charge right here, this number 2 goes for the entire thing. So what you have to do is to bracket that one. All right, so that's why we have calcium 3 over, and then we have PO4 bracket, and then the 2 that came over, it is saying that we have two molecules of the phosphate ion. All right. I know that I say use the word molecule of phosphate because phosphate is a molecule. All right, not an element. I could say we have 3 atoms of calcium. Okay. So here it's saying we have 3 atoms of calcium, but 2 molecules of the phosphate group. Because once you have more than 1 element, it is a molecule. All right? All right. The next one here is aluminum and oxygen. Again, the same example we did before, but this was in the using the cation and anion form. Again, just cross it over like that. Drop the numbers down. And then what we're going to have here is Al2O3, aluminum oxide. All right? All right, another one here. Again, you can work this one out. I'm going to drop it down for you. Just look and observe right there, and you know exactly what to get. Jumping through real quick. There's a next example right here again. Drop the numbers across. All right, work them out quickly, and that's your formula. All right, again, once it's a polyatomic ion, you have to bracket it. One's going to carry a number over. For example, the 2 went over for the ammonium ion, so therefore you have to bracket the ammonium. All right, just remember that. All right. Covalent bonding. And covalent bonding can go in 2 ways. All right, so we're going to do that real quick. All right, again, for covalent bonding is the sharing of electrons between non-metals, just to point it out real quick. All right. So again, in different from ionic bonding, where you transfer electrons over from metals to non-metals, in covalent bonding, you actually share the electrons, and you're sharing the valence electrons. And I point to note that only valence electrons take part in chemical bonding. All right, or chemical reactions. Only the valence electrons do that. All right. So here now is that we're going to look at only one type of non-metal, and then we'll go to the different types of non-metal real quick. All right. So first you have to know, again, you have to know the valence electrons. Just remember that, and you have to know the amount of electrons needed to achieve an octet, which is mean a full shell. So those are the first 2 things you need to know. All right, and then we're going to jump into now the example. And so let's say we're bonding oxygen to itself. Again, you must know the valence electron, which is 6 in this case. Again, oxygen has 8 electrons. If you don't know, look at the periodic table. 8 electrons, so therefore it's 2 and 6 for the electron configuration. The first shell is always 2. The remaining go on the second shell, maximum 8 on the second, maximum 8 on the third, maximum 8 on the fourth. All right, so now we know this. Each oxygen has six valence electrons. So therefore, each of them require 2 more electrons. All right. So what we're going to do is to bring them together and share the 2 electrons that each need. So notice that I took 2 from the red side and 2 from the blue side. So they are sharing these 4 electrons together. All right, just to make a point right there. All right, and that's O2. That's the oxygen we need, oxygen gas we need to survive, to breathe, and respire. Now again, let's say N and N. The electron configuration is 2 and 5. 5 is valence electrons. So therefore, put them together. Each of these will need 3 more to be full or reach 8. And so when they come together to share, what they're going to give is 3 each. All right, and if you notice, around each of them is a total of 8, right? Around each ring or shell, you have a total of 8. But the idea, each of them give the other what is required, okay? All right, and this, matter of fact, this is only applying for when the elements or atoms are the same. So therefore, nitrogen bonded nitrogen, and this is a triple bond, by the way. This is a triple bond, just to make mention of that. I will talk about that in a little bit later as well. All right, and that is the nitrogen gas or nitrogen molecule. All right, and a type of bonds form, which I'm going to talk about, the single, double, and triple bond right now, real quick. So we have single bond is when you only have a pair of electrons being shared. All right, so that there is a single bond and you only have a line for a single bond. So a single bond represented by a single line. We also have a double bond, and that's when 2 electrons are shared from each element, which means a total of 4 electrons, 2 pairs of electrons. And so therefore we have 2 lines representing that. A triple bond is when we have 3 pairs of electrons, or a total of 6 electrons. Hence we have here 3 lines, okay? So that's a single, double bond, and triple bond. We don't have any more bond, only single, double, and triple bond. That's for covalent bonding, by the way. So for covalent compound, it can be single, double, or triple bond. All right? So you don't refer to bond in ionic compounds. No, don't do that. All right? So for example, fluorine and fluorine, that's a single bond. So if you draw it like that, it become a single bond, just to make mention of it, but you don't draw the line in the ring shape or the dot and cross form. They don't do that. So you draw it by yourself down there. Notice it at the bottom. That's the example. You do the single bond thing right there. All right, and so let's go to the next example now for a double bond real fast. Oxygen and oxygen form double bond. Again, notice that the 2 lines are there for a pair of electron, each line for a pair of electron or each bond. All right, and so oxygen to oxygen, we can draw it like that. At the bottom right there, that's the structural formula there. All right. All right, and let's go to the last example here now, which is nitrogen and nitrogen. So again, they share 3 electrons each, so therefore we have 3 pairs, and each pair is a bond, and so there we have a triple bond between nitrogen and nitrogen. All right? All right, so let's jump past that now into covalent bonding, but this time we're using different nonmetals. All right, so this one's a little bit more challenging for most persons. All right, so when you're doing covalent bonding, for example, bonding water, how do you achieve that? All right, and so there's a little thing I follow, a little format that I have here. All right, again, covalent bond is sharing of electrons between nonmetals. We don't need to go back over that. We've already been through that. Again, we need to know the valence electrons. We need to know the amount of electrons needed to form that octet or that full shell. And we also need to know the number of each atom needed. All right, and so for a typical example, I'm not going to go through all of them. I'm going to skip over some. All right, and so we have H and O, for example. So you can just make a little outline and say, okay, the valence electron. So for H, we only have 1 valence electron, which is the only electron, by the way. And oxygen has 6 valence electrons. All right, and so we keep hydrogen on the left and oxygen on the right. And so valence electron therefore for hydrogen is 1, for oxygen is 6. The amount of electrons needed for hydrogen, which is special because it is first shell. First shell only has 2 electrons. So okay, can I put 7 there to make it 8? Because this is the first shell of in hydrogen. So the first shell holds 2, so you only require 1 more. For oxygen, there are 6 valence electrons, require 2 more to become 8. And now to determine number of atoms, what we're going to do is to crisscross these numbers again, as we did in ionic bonding, but it's not the same. So just crisscross numbers over. All right, and so we need 2 hydrogen and we need 1 oxygen. All right, again, here, this represents the lowest whole number ratio. So the number of atoms represent the smallest or the lowest whole number ratio, or just the whole number ratio between the elements, right? So again, based on this, what we're going to have here is 1 oxygen with 2 H's covalently bonded together. Hydrogen only forms single bond, by the way. All right. And that's water that we can't live without, or H2O. All right. C and F. And now after this, I'm going to skip the rest. All right. So C and F, for example. So carbon has 4 valence electrons, fluorine has 7. So we put the 4 there for carbon, 7 for fluorine. How many electrons is needed to become 8 for carbon is 4 more. How many required to become 8 for fluorine is 1 more. And then, of course, we're going to crisscross those over. So we need 1 carbon with 4 fluorine. All right. And so when we put them together like that, carbon is the central atom in this case. The one is the lowest number is always the central atom. So you put carbon first, attach with 7 fluorine onto that, and then we're going to draw on your electrons accordingly. Again, what you need to know here in terms of what you put in the bond is based on the lowest number that is needed. And so fluorine can only form single bonds. All right. So you put only single bonds there. And you put a single bond is a pair of electron, by the way. All right. So fluorine, group 7 elements can only form single bonds. All right. And so we have that, put on the extra electrons there for fluorine. Remember, fluorine started out with 7, you know. So fluorine started with 7 and only gave up 1, you put the 6 on the outside, right? We call those the lone pairs of electrons. All right. All right. And so the structure could be like that as well on the left. So you can look at it on the left. That's what the structure look like. 4 single bonds. All right. With chlorine in the middle, carbon in the middle, and fluorine around the parameters. All right. All right. So the parameters, I said. All right. So again, this is called carbon tetrafluoride or tetrafluoromethane. We talk about that when we talk about organic chemistry in a little bit. All right. Now, this on the next one right here, again, I'm going to run through real quick, so you can just go through and learn the concept. You could try it on your own and make sure that you understand how to bond covalently. All right. So just follow the concept and see exactly what I'm going through. You can always slow down and observe it. All right. So that's a double bond right there, okay, between S and O. Carbon dioxide is a special example here, so I'm just gonna kind of go through it real quick with you. All right, so up to this point you should be okay. So here we have 2 and 4, and here we say we need the lowest possible number right here. 2 and 4 is not the possible lowest number because you can divide 2 by 2 and 4 by 2, you get a lower number, which is 1 and 2. But if you follow this method, you should have 2 carbon with 4 oxygen, but again we can go lower because both of them can be divided by 2. All right. All right. And so carbon dioxide will just be CO2. All right. So it just be CO2. And again, we only have double bonds right here based upon this number of electrons needed. The lowest number needed here is 2. That means we're going to form double bonds. All right. All right. So those are double bonds there. All right. So I hope you mastered that part so far. All right. Now let's talk about chemical reactions real quick. All right. As we trod as quickly as possible through this. Now, chemical reactions, again, is just a reaction between elements or molecules or compounds, right? The things that are reacting, we call them reactants. Those at the end, we call them products. All right, and I know that at least most of you, or if not all of you, should know about chemical reaction by now. That's why in chemistry. Unfortunately, if you didn't have a teacher, then I'm very sorry. I know. Goodly, maybe you could pick up 1 or 2 things here, but I really have to go fast. All right, so we have the reactants and we have products. All right, the arrow means to produce. All right, just to mention that. No, chemical reaction is really the process by which chemical substances are chemically transformed into different chemical substances. So the idea between a chemical reaction is that a new substance must be formed. You cannot get about the same thing. It has to be a different substance, right? Now, what takes place here for chemical reaction to take place is that old bonds are broken and new bonds are formed. Very important. You break old bonds, you form new ones. That's why you get something new. All right, so what you produce, you get this thing is called product, and this product is a new substance, different from what you react with. So it's different from the reactants, all right? All right, so now we call this a reaction box, just to kind of give an idea what's going on here. Because truthfully, if you have A and B going together and they go into the reaction box, not a real reaction box, really, they're going to go into react again is something new. So A and B they go in, what you get out is AB, something new. So reactants are different from products. That's our demonstration right there, okay? All right, let's jump over that thing. All right. Now, reading a chemical reaction again, you must know reactant from product. For example, A plus B or A react with A, B, C. So A reacts with BC to produce, arrow means to produce. And what you get as a product is a product A and product B, for example, or product AC and product B, So that's how you read a chemical reaction. Those are just introductory stuff. Persons who just start in chemistry. All right. Now we also need to know about state of molecules or substances in a chemical reaction, and the state, we call them state symbols, and the state symbols will come to the base of the thing, the subscript. So for example, we have G for gas, L for liquid, and AQ for aqueous, and S is for solid, all right? So you need to know those, all right? So G for gas, L for liquid, AQ for aqueous, and S is for solid. All right, now types of chemical reaction real quick. All right, so we're going to jump into types of chemical reaction now. The type of chemical reaction you have to learn right here, we have combination reaction, decomposition reaction, single replacement reaction, double replacement reaction, and combustion reaction. Combination reaction is also called addition reaction. All right, so don't be scared of the word now. So combination or addition reaction means the same thing. All right, all right, all right. So running through real quick. Combination reaction is simple when you add stuff. All right, so I'm just going to quickly add A and B. For example, get AB. No need to hang up on that one. Very straightforward, very simple. That's addition reaction or combination reaction. Typical example for this, let's say you have sodium reacts with Cl, come together, get NaCl. That's just it. And you need to know how to balance the reactions now. That is a must. Balancing chemical equation, all right, is a must. All right, so of course, we're going to put 2 in front of NaCl to make it 2Cl as a 2Cl in the front, and then 2 in front of Na. So we have 2 of everything on either side, all right? Sodium is a gas, sodium is a solid. Where get that nonsense from? Sodium is a solid, chlorine is a gas, and NaCl is also a solid, which is salt. All right, that's table salt. It's salt that you eat with, all right, or you cook with. All right. Now, jumping on now to another type here is decomposition. That's not about decomposition, it's breaking down of something. So you're going to decompose here, and so when you're going to break down, and this is when a compound breaks down into 2 or more simpler molecules. That's decomposed. It gets simpler by breaking down. Normal energy is required for this type of reaction. All right, so even if you don't use energy, well, technically going to use energy because even light is an energy. Electricity is also an energy as well. It's electrical energy. So energy is required in maybe in different form, but energy is required for decomposition reaction generally. So for example, you have AB. If you decompose AB, you should get A plus B, right? So those are the products. A and B are the products from AB. All right, now let's look at a typical example right here. So for example, we have aluminum oxide, all right? And I really love aluminum oxide as one of my favorite compounds to bond, to be honest. Now if I break this down or decompose this, what I'm going to get is aluminum, which is the metal, and I'm going to get oxygen, which is the gas. And so we have aluminum oxide, break down into aluminum, and so we're balancing the chemical equation right here. So you need to just practice that. Make sure everything is equal on both sides of the equation. All right. Those are the state symbols. Aluminum oxide is a solid. All right, is really a corrosive form of aluminum. The corrosion of aluminum, I should say, not corrosive, but corrosion of it. All right, so it is oxidized. All right, and then we have aluminum. It's a solid, as you know. Oxygen is a gas. All right. Now, simple replacement reaction here. Single replacement reaction. And single, one thing is replacing another thing. All right, we have double coming up shortly. So single replacement is simple. A single displacement is when you only use one simple element replace another element, right? And so, for example, if you have A and then plus BC, A can replace B, right? So A replace B, a single element replacing something. So what you get there is AC and B by itself. So A replaces B. All right. Now, a typical example here as a real element or molecules, we have magnesium reacting with HCl, which is hydrogen chloride or hydrochloric acid. What you're going to get here is magnesium replacing hydrogen or displace it. And what you get here is MgCl2, which is magnesium chloride. And we have hydrogen gas, all right? All right, again, balance the chemical equation, put on the state symbols as best as you possibly can, especially if they ask you for them, all right? All right, double replacement now is 2 things replacing, as you know. Now it's double, so it's 2 different elements replacing each other in a chemical reaction, all right? So what we're going to do here now is just to show you real quick as the notes finish loading on this screen. Again, usually we say water, salt, a precipitate, or a gas is formed. So those are the things that normally form from a double replacement reaction. You get a salt, you get water, you get precipitate, or some form of gas. All right, for example, if you have AB plus CD, all right, again, it's double, so they're replacing each other. All right, so two things replacing each other. So A can replace C, all right, and C replace A, all right, or D replace B, in other words. So what you get here now is AD, and you also get CB, all right? That's a double replacement reaction here, typical double replacement. Now, an example right here is BaCl2, all right, barium chloride. Now, it reacts with magnesium sulfate, all right? What we're going to get here is barium sulfate and magnesium chloride. And of course, you know that barium sulfate is a precipitate, white precipitate, right? All right, that's why it's a solid right here. And so those are some of the things that you need to know. Magnesium chloride is a soluble salt, so it could dissolve in water. That's why I get aqueous, AQ, all right? And two aqueous substances can produce a precipitate, which is a solid, and also another aqueous solution. Combustion reaction, as you know, is burning of anything in the presence of oxygen. All right, so burn anything in the presence of oxygen, that's combustion reaction. All right, so all organic substances tend to combust in the presence of, well, most of them combust in the presence of oxygen, especially those that are in the homologous series of alkane and so on. All right, especially simpler ones, actually. All right, so combustion reaction, again, if you have A plus oxygen, what you're going to get is carbon dioxide generally. You get water and you get energy. So those are the three things you get from a combustion reaction: carbon dioxide, water, and energy. However, if it is incomplete combustion, you get carbon monoxide instead. Okay, if it's incomplete. For complete combustion, if it does say combustion generally, it is carbon dioxide. If it's incomplete, it's carbon monoxide. All right. And so that's a typical example right there for us. So a combustion reaction, again, methane combusting in the presence of oxygen. What we're going to get here again is carbon dioxide, water, and some energy. All right, to balance the chemical equation, the state symbols must be placed there. All right, and again, we get energy some way. All right, now reactions of acids now. Jumping on to this one, reactions of acid. Now, there are a number of different types of reaction where acid is concerned. All right, we have acid plus metals, acid plus metal oxide, acid plus base or alkali, acid plus carbonate, acid plus hydrogen carbonate. All right, so those are the five basic acid-base reactions that you must know, or at least familiarize yourself with. All right, so let's talk about acid plus metal real quick. Again, I'm just jumping through as fast as possible. Please, I'm sorry for that. I really want to finish so you could get this before the exam. All right, so acid plus metal give us salt and the gas of hydrogen, so hydrogen gas. All right. Typical example here: magnesium plus HCl, which is hydrochloric acid. What they're going to get here is magnesium chloride plus hydrogen gas. And you need to know the test for hydrogen gas. As a matter of fact, hydrogen test with a popping sound. So you put something, a fire or a little splint in the presence of hydrogen, you're going to give a popping sound. All right, or explosion. You will get the mark for explosion, but a popping sound is the better way to say it. All right. I balance against state symbols. I just try to do it as best as I possibly can. Now, how do you know if a metal can react with an acid? It's simple to know its reactivity series of metals. And so all of this on the left, they are more reactive than hydrogen. So they can replace or displace hydrogen in an acid. The others, which are copper, gold, silver, and platinum, those they are less reactive than hydrogen, and so they are more difficult or almost impossible to replace hydrogen, all right, in a chemical reaction, unless it's under heat or using steam, for example. All right. All right. So just need to know that the ones on the left can replace H, but the ones on the right cannot replace hydrogen in a acid. Now, just a way I came up with this to kind of remember the placement of these is please, and please is for potassium, but potassium is a K, as you know that. All right, so please, and S is for sodium, just by the names, and C is for calcium. All right, but of course you can come up with something better. All right, with this to remember, let's not even waste time on that. But you can just come with a nice acronym if you want to remember the reactivity series. That's just mine. All right. Now, example here, silver. If you have gold, for example, if you have silver, gold, platinum, they don't react with acid. So you can clean jewelry, for example, like gold that we have here now. You can clean gold with acid and it take off all impurities and leave the pure gold behind. If it's not pure, then you can't use acid to your jewelry become black because they're going to react and oxidize, right? All right, so it's impossible for gold to replace hydrogen. So no reaction will take place in this sense, all right? Again, it must be more reactive to cause a reaction. All right, so that's another example here as a reminder. All right, acid plus a base or alkaline. Acid plus base or alkaline, what they get is salt, water. All right, salt and water. All right, quickly let's run into this. For example, magnesium hydroxide react with sulfuric acid. What they're going to get here is the magnesium replacing the hydrogen. So what they're going to get as a result is magnesium sulfate and water. All right, again, balance the reaction. Oh, I jump over that a little bit too quick, so you can see the balance reaction right there. All right. So once you see the balance reaction, we're good. All right, so now go back now to acid and metal oxides. It is similar to alkaline. Once acid reacts with a metal oxide, what they're going to get is salt and water. So it's similar to alkaline or a base, pretty much similar. All right. Typical example right here is calcium oxide plus HCl. What you're going to get here is calcium chloride and water. Matter of fact, let me just quickly tell this. How do we know there's going to be CaCl? Chlorine is in group 2, so it's a 2 plus. Sorry, not chlorine, I said chlorine. Calcium is in group 2, so there's a 2 plus. Chlorine is in group 7, so there's a 1 negative, all right? All right, I'm going a little bit fast, so yeah. All right. All right, so now acid plus a carbonate. So acid plus carbonate, what you're going to get here is acid plus carbonate, you're going to get salt, water, and carbon dioxide. All right, so those are the three products if an acid react with a carbonate. And an example right here is potassium carbonate reacting with sulfuric acid. What you're going to get here is a potassium replacing the hydrogen. So you're going to get potassium sulfate with water and carbon dioxide. All right. Now, acid plus hydrogen carbonate is similar to a carbonate, but what you're going to get here is a little bit different because you have hydrogen within the carbonate. So you're going to get a salt, you're going to get water, and you're going to get carbon dioxide, similar to a carbonate. However, sometimes you can form what they call acidic salts. Sometimes, all right, depending on which one you're using. All right, so we have acidic salts can be formed as well. All right, in some cases. All right, so sodium bicarbonate. All right, and of course, you know that we have a baking soda. All right, so we get sodium chloride right here, get water, and we get carbon dioxide. So that's a typical salt right there from that. The Na replaces the H. We get NaCl with the sodium chloride, water, and a carbonate. Again, you can have something called acidic salt, but typically you get salt, water, all right, and carbon dioxide. Now titration. All right, so we're getting it closer and closer as we go along. Right, it's kind of long, but I know the chemistry is just like this. Titration is also called volumetric analysis, right? Titration is the same thing as volumetric analysis. Now, in titration, what you're going to use these are basic things like a pipette, burette, titrant, analyte, and an indicator somehow. All right. The titrant must have a specific molarity. That's why I have this on label, which is called a titrant. All right. The analyte is something that you don't know nothing about, just to make mention of that. All right. So let's jump through as fast as we possibly can. So again, titration is a process by which a standard solution, which is called a titrant, is slowly added to a solution of unknown concentration. We call it the analyte, okay? Until the endpoint, or endpoint is reached. How do you know what endpoint is reached? It could be a neutralization point, as we also call it. And this is done by using an indicator. All right, so indicator tells you when you reach an endpoint. All right. And the reason why you do a titration process is to determine the concentration of an analyte or an unknown substance. So when the substance is unknown, you use titration to determine those the concentration. All right. Now for step 1 in a titration, you're going to fill the burette with the titrant, and you're going to fill it as way up to the top, of course.
and they're going to release your volume after. But notice I have a specific molarity there, example 0.33 mole. All right, let me just speed up through this real quick. Second thing you're going to put, once you do that, once you have your titrant, right? What you're going to use now is a pipette to transfer the specific volume of the analyte into a flask. You need a specific volume of that analyte because your thing is already burette, which is a titrant. The analyte going to be in a flask at this point. You transfer a certain amount, release it into it. All right, and then after you have done that, you're going to add a few drops of indicator into the analyte. All right, the indicator will tell you when the reaction is complete. All right, and so you have acid-base titration. It's very important for you to know those. All right, those are the most simpler ones. All right, and so you're going to use the burette now to slowly add the titrant into the analyte containing the indicator, and then you're going to also swirl, just slightly swirl as you pour it all around. And the reason why you swirl is to make the titrant evenly distributed in the flask, so you can have an even reaction. All right. So while you do that, now the indicator will change somehow, right? So the indicator going to have a change or disappear. So as soon as it disappears, at the point when it disappears, that's the point where the reaction has end or reach its end point or its neutralization point. All right, if you do an acid-base titration. Now for step 6, you will record the analyte in terms of the amount of analyte you use, the volume of analyte you use to cause the reaction to occur. And trust me, titration is linked to quantitative analysis. All right, so they are linked together. So quantitative analysis is linked to titration, but titration is linked to it. Because once you know how to analyze things quantitatively, you can do titration really easy. All right, so a quick formula that we have here to work out this thing is that MA over MAVA over NA, and just to make a note, I have this on the next screen anyhow, that MA, it is the mass of the acid, and V is the volume of the acid, and N is the number of moles of the acid, right? There's a simple formula to work out titration, acid-base titration, by the way, and it's equal to MB VB over NB. All right, and point to note here again, M represents mass, V represents volume, and N represents number of mole. The A's represent acid, the B's represent the base. All right, so it's an acid-base titration. Again, let me just do that real quick. I'll been through them, not to be too fancy right now. All right, but those are the stuff here in terms of meaning. Again, you can pause, take a screenshot of that or whatever it is and know it. All right, so again, M represents molarity. All right, and you have two types of molarity. You have mass molarity and you have, well, I say it wrong, matter of fact. You have two types of concentration. But when you have M, a big M, uppercase M, is represent molarity. Okay, so the molarity of the acid, molarity of the base. And I think I said mass in my head somewhere, you know. I think I'm moving too fast. Yeah. So the concentration could be of two types. Mass concentration, that's what I really should have been saying. You have mass concentration and molar concentration. But a standard concentration is now represented in molarity, which is molar concentration. All right. Yeah, so that's the correct version there. All right, goodly. I catch myself. All right. So molarity again of the acid, which is Ma, Va is volume of the acid, Na is the number of moles of the acid accordingly, and the B's are for the bases, all right, or the base. Now again, given this example right here, if it takes 10.5 ml of a 0.25 molar concentration of hydrochloric acid solution to neutralize 300 ml of sodium hydroxide solution, what is the concentration of sodium hydroxide solution? Sodium hydroxide is the base, by the way. So they give it the volume and molarity of the acid, but only give it the volume of the base. So we know that the acid is the titrant and the base here is the analyte, all right? And so all you need to do is plug them in the equation accordingly, all right? So again, plug them in the equation, but before you do that, you have to work out the balanced chemical equation, by the way, just remember that. So work out the balanced chemical equation first. This equation is balanced as it is. So we're going to plug in the information of our acid, molarity of acid, multiplied by the volume of acid, divided by the number of moles based upon the balanced chemical equation. And we will have 1. And we do the same thing for the base. All right. And notice that the molarity of the base is not known. And they're going to change, make MB be the subject of the formula. And we work that out. And then I jumped the gun too quick. Sorry. Let me go back 1 second. My mistake. Yeah, right here. Right. So this is the molarity now of the base, which is 0.0875 molarity. This is molar concentration. All right. Yeah, let me emphasize that. The M here, uppercase M, is molar concentration. All right. So that is the molar concentration. Look at the formula, look at the workings, and you're good. All right. They're color coded, make it life easier. All right. All right. Now talk about oxidation state and oxidation number. I'm going to talk about the rules now. Oh Lord, I don't have any examples in terms of calculation, but just to know the basic rules for oxidation state, oxidation number. And basic oxidation number, you will know them directly because oxidation state, all right, it refers to the total number of electrons that were lost or gained by an atom when forming a molecule. So it says a lost or gain of these electrons when forming a molecule. So of course, once you understand it, and we did talk about metals and non-metals earlier, we should know that the elements, based upon their groups, right? Based upon their groups, they give you the oxidation state. So the first one you have to know about all elements. Elements in their pure or uncombined state have an oxidation state of 0. All right? Because of course there was no loss or gain of electrons if it's just in the natural way, right? So therefore 0. All right, so for example, sodium, calcium, oxygen, and aluminum, they didn't lose or gain anything. So yeah, oxidation state 0. All right? And again, the reason for that is that because the number of protons also equal number of electrons as well. Remember, talk about the elementary charge of all elements in their pure form. We talked about that a little bit earlier. All right. So again, next rule you need to know is that the total oxidation state of an atom in a compound equal to 0. So the total oxidation state of all elements within a compound is equal to 0. So for example, Na2CO3 has a total oxidation state of 0. Total, notice the keyword here, total. When you add up everything, it should be 0. All right? So even though electrons are being transferred, it is still equal to 0 because what was gained equal to what was lost. And so the positive charge equal to negative charge is just the same, right? All right. Another rule here that you need to note is that elements of group 1, 2, and 3, I say group 1, 2, and 3 assign oxidation state of positive 1 and positive 2. And of course, most of those in group 3 as well as positive 3, respectively. All right. So they have the same oxidation state or oxidation number according to their valence electrons. All right. All right. And just to make a note right here, and the reason for that because they're electropositive, all right, and will lose electrons to form cations. Group 3 does it will do the same. All right, those elements will do the same. All right, but of course, you know the rules are a little bit change as they go across. All right, because it moves from metal to non-metallic property in terms of loss and gaining. Now the next one here is that the total oxidation state of all the atoms in a monatomic or polyatomic ion is equivalent to the charge on the ion. All right, so for example, we have NH4 plus, the total oxidation state here, notice the keyword here, total, the total oxidation state of Na4 plus is +1, for SO4 2 minus is -2, and for PO4 3 minus is -3. So the total oxidation state of any ion is equal to the charge on that ion. All right, whether it be monatomic or polyatomic, doesn't matter. All right. Next thing on our list right here now, again, we still got the next rule. I think we have about one more rule to look at, really. So oxidation state of fluorine, for example, is always -1. And you know why? Because fluorine is the most electronegative element. And therefore, it always pulls a single electron towards itself, no matter what bond with it. It is the most electronegative. So you're gonna bully every other, for relative use word bully, but once it bonding with anything else, with any other non-metal, it's gonna pull electrons away from that non-metal to itself. So yeah, let's call it a bully. So fluorine is like a bully of electrons, pull electrons toward itself. Yeah, that's what it is doing. All right. So again, we have some example here, like CF4. Again, fluorine will pull electrons to itself because it's more electronegative and always gain that single electron from the element. So for example, CF4, fluorine will pull electrons from C. And so a rule, if you follow the rule, you realize that in CF4, the oxidation state of fluorine is -4 in total, right? Because there are 4 of them, 4 of them. So it's going to be 4 in total. And And carbon will be a positive 4 because it lost 4 electrons to each of the fluorine. All right, so carbon in this case will be positive 4. All right, and fluorine will be negative. Each of them will be negative 1, so a total of negative 4 in total. All right, all right, all right. So where we at now? All right, so we're gonna sixth rule. I think this is the last one. So oxidation state of hydrogen is usually positive 1, except in metal hydrides. All right, so normally it is positive 1, but when in metal hydrides, it is different. So for example, fluorine and hydrogen, again, fluorine takes on 1. Again, it is more electronegative than H, and H will lose that one to become positive. So therefore, hydrogen is positive 1 in that case. But they want to form a metal hydride. So notice is metal. Lithium is a metal. Fluorine is a non-metal. So when hydrogen bond with a metal, it gains electron. So gain that single electron and become a negative 1. All right? Yes. But in, for example, for fluorine or any other non-metal, hydrogen tends to be the one that will be more electropositive and lose electron towards the other non-metals and become what? Positively charged. All right? All right. So that's just the notation here that I just been through just now, pretty much. All right, let's jump over. All right. So I'm going to skip over the example that coming up after this one. So there's only talk about that. The oxidation state of oxygen in a compound is usually negative 2, as you know that, except when it's in peroxide, and that is, you don't get much of that in the exam, to be honest, so you don't need to worry about that too much. Bonded with F, with this fluorine, it becomes positive 2 and so on, right? Or bonded oxygen and fluorine, so an oxygen bond to fluorine becomes a positive 2 instead. All right, let's talk about heat curve real quick. All right, so heat curve. Now, heat curve of water, that's something that you need to know. Heat and cooling curve. So let's talk about what happened here quickly. All right, so what we're going to look at here is the principles. We want to talk about some demonstrations real quick, and then we talk about the graphs. All right, so we're going to do that really quick. So when we talk about heat curve, we talk about loss of energy or loss of heat or gain of heat to change the property in terms of state. All right, so particles, need to know particles are always in constant random motion. All right, so you need to know that particles are always moving. All right, the next thing you need to know right here is that the kinetic energy is proportional to what? Temperature. And you need to know that because as temperature increases, particles move faster. Yeah, they gain more energy and move faster. All right. Now, the next thing you need to know here is that a loss in kinetic energy is a gain in potential energy. All right. So gain potential energy and lose kinetic energy. All right. All right. Next thing you need to know as a concept is that as particles gain kinetic energy, all right, they move much faster, which I mentioned earlier, and they eventually break away from each other. So the more energy they get, the faster they move, they break away from each other. They break that bond. All right. And of course, you cannot go after a certain point when the temperature is reached, you know. All right. One more point here is that temperature remains the same during a change of phase. Please don't forget that. Once you have a change of phase, which moving from solid to liquid or liquid to gas, or vice versa, temperature remains the same. Okay? That is why ice water is as cold as ice when ice just melts. Okay? They're the same temperature. Solid ice, that's the solid ice. Solid water, which is ice, is the same temperature as ice when it just melts. All right? So again, just watch the temperature on the fire source right here, the heat source. As it goes up, what's going to happen here is that these particles are going to move much faster. All right, so the particles move much faster as heat energy increases. That's a demonstration. Let's move over that. Now let's talk about this ice melting, yeah? So ice is at -0 for -10 degrees Celsius, for example, right? What happened to this ice? It will reach to its freezing point, which is a standard of 0 degrees Celsius. Notice it is solid to solid. All right, solid to solid. All right, so what happened there is a solid state. Now notice this. Notice that just go back a little bit. Notice there's no change of state. The state is the same, solid to solid, no change of state, but it's a change of what? temperature. So if temperature is changing, the state should remain the same. Please remember that. Don't forget that at all. No, look at this. 0 degrees Celsius now, ice, right? That's a standard freezing point of ice, pure water. Now, when that starts to melt into liquid water, what temperature is that liquid on the ice? Still 0 degrees Celsius. Now, there is a change of state from solid to liquid. So once the state is changing, the temperature remains the same. 0 degrees Celsius ice to 0 degrees Celsius water. The state remains the state. The state changes, but the temperature remains the same. All right? So again, it moved from melting point to freezing point. All right? Now we have the water at 0 degrees Celsius, ice cold water, we call it ice cold water, 0 degrees Celsius, right? Now, if it could change between a range of temperatures, it could be 20, 40, 60, whatever, it don't matter. So it changes to a range of temperature until it reaches its maximum temperature, which is the boiling point. So what's going to happen is that you have a different temperature range. The change of temperature could range so small or so large. However, at that last point, the water will start to boil, which is at 100 degrees Celsius. Pure water boils at 100 degrees Celsius. Now, what's going to happen here now? There is a change of temperature, but the state remains the same. Still liquid water at 0 degrees Celsius. Still liquid water boiling, right? Temperature remains the same, liquid to liquid. Now, if you have this liquid boiling at 100 degrees Celsius, what's going to happen here? You're going to steam up and give off steam. When steam is given off, it is still 100 degrees Celsius. Therefore, the temperature remains the same, but the state is changing from liquid into a gas. All right? Liquid into a gas. That's what is happening there. So again, please note, when the temperature remains the same, right, there's a change in state and vice versa. Now let's look at the graph real quick how to draw a heating curve for water. The cooling curve is opposite, of course. You're coming down the line. So the first thing that we started with negative, and typically they could give a 0 degrees Celsius ice, right? But I just put minus 10 just to make it a little bit interesting. So what's going to happen, I'm going to carry you to 0 degrees Celsius. There's a change, but there's still a solid, still remains solid. Now what's going to happen here now is that we're going to have this 0 degrees Celsius water, right, that does melt. It's going to be liquid into solid into liquid, by the way, right? So it's melting taking place, right? And so it's moving from 0 degrees Celsius all the way over, and then they're going to change now. The temperature is going to change, and if temperature change, the state will what? Remain. All right? The state will remain. So notice at our 0 point, it is here solid at this point, then it comes to liquid at 0. Solid into liquid, no change of temperature. When we move from liquid into when we move now from a liquid into a gaseous form, then you're going to have a temperature remain the same. Here we have a temperature changes now from 0 into 100. The liquid remains the same, still liquid. From 0 degrees Celsius water into 100 degrees Celsius water, no change of state, but a change of what? Temperature. All right, so temperature and kinetic energy increase. Now moving from the 100 degrees Celsius, continue to 100 degrees Celsius. That's now boiling taking place right there, and it turns the liquid to gas. The state is changing, the temperature remains the same. All right, and of course, if we go further than 100 degrees Celsius, it's no longer gas, but maybe become plasma. All right, and so this here is your cooling curve for, not cooling curve, heating curve for water. All right. All right, and that's the information they're presented right there. You need to know something like that, just in case you may see something. All right, extraction of metals. Now jumping onto that new topic I'm going through. This is never ending, and I understand. Now I'm looking at iron only. You need to know how to extract aluminum as well. All right, so looking at iron, and iron comes from its ore, which is called hematite, and hematite is iron 3 oxide. Just to make mention of that. All right, and so oxygen is needed for combustion of carbon and heat production. All right, limestone, all right, or calcium carbonate reacts with acidic or acidic impurities, forming molten what they call slag. You need to know that as well. All right. Carbon, which is coke, carbon, which is called coke, it combusts in the presence of oxygen to form carbon dioxide, then form carbon monoxide. So this information is steps technically I'm explaining. And then carbon monoxide now reduces the iron 3 oxide, right? All right, so these are the steps. Step 1, you have hot here, which is oxygen plus coke. You get carbon dioxide right there. That's the first step. The second step here, we're going to have here is carbon dioxide now reacting with coke to give a carbon monoxide, and this is a reducing agent, right? So that becomes a reducing agent right there. Now in step 3, you have iron 3 oxide that is formed, react with coke again. You get iron. Notice you have iron by itself now and carbon dioxide. Or if it's within the blast furnace, which is a very expensive method, what you're going to have here is the iron 3 oxide in the blast furnace reacting with carbon monoxide, and what you're going to get here is iron, all right, and carbon dioxide. So similar to the one up top, so either or either, but of course one on top is the most popular one that you will see. This step 4 right here is really to remove impurities from the process. You're going to add calcium carbonate, and calcium carbonate will form carbon oxide and carbon dioxide. All right, and then you can have here is carbon this calcium oxide that was formed right here. You react that with silica or silicon dioxide, which is from sand or made sand, and you get what is called calcium silicate. All right, and that's how you remove the impurities from the process of removing iron from its ore. All right, carbon compound, organic chemistry time now. All right, so carbon compound is a quick introduction to carbon compound. Again, there's a number of things you need to learn here. I'm going to skip over certain things as quickly as possible. Again, carbon is unique, so carbon can form many covalent bonds. It can form 4 single bonds, for a total of 4 single bonds. That's very important for us to note. All right, it can also form a double bond between itself. It could form triple bond with itself. So that's what makes carbon compound so important. So it can form 4 single bonds. It could form double bond with itself. It can form single bond with itself. It could form triple bond with itself. That's make it unique. Matter of fact, carbon is the backbone element in organic compounds. All right, that means it is also the fundamental element that make up living things. Right. Now, the bond between carbon atoms, for example, carbon can form single bond, double bond, or triple bond with itself, right? So carbon can form those 3 types of bonds with itself. So it's very unique. All right, again, to understand this, there must be 4 maximum single bonds around any given carbon in any given compound, no matter what compound it is. There has to be a total of 4 single bonds for each carbon. When I say a total of 4 single bonds, it could be in any combination. So let me just show you real quick. So you can have it like this, separate single bonds, 4 separate single bonds, or you can have this is a single bond, that's the same. So single bond between itself or single bond. Let me just jump to the double bond one. All right. So on a double bond case, it's like that, and then you put on the others. So notice that there are 4 lines around every carbon, which means 4 single bonds in total. Triple bond, you can only put 1 more line on the outside, right? All right. Now, important points to note right here is that carbon forms covalent bonds. Just to make note of that. Carbon can bond with itself and other non-metals easily. Carbon group 5 elements can form triple bonds with carbon. Just to make mention of that, because how we know it can form triple bond? Because each group 5 element requires 3 more electrons, which means they can form triple bonds. Point to note, it can form not only triple bonds, it can form double and single bonds. So group 5 elements could form triple, double, or single bond with carbon. Group 6 can form double and also single. Group 7 elements can form single only with carbon, only single bonds. So group 7 elements, halogens, can only form single bonds. All right, let's talk about alkanes real quick. Now, alkanes, and we're going to wrap up real fast, all right? I think I have, I think three other series after this. So this is alkane homologous series. And alkane now, they are a special homologous series, which is the first and primary homologous series of organic compounds or organic chemistry. And so alkanes now are a group of hydrocarbons, organic compounds, which are organic compounds consisting of only single bonded carbon atoms. So between the carbon atoms, there are only single bond in alkanes. Now, the general formula for alkanes is CnH2n plus 2. What N is the number of carbon. Okay? So the formula is based upon the number of carbons. So I'm going to show you that real quick. All right. Now, for example, notice there are only single bonds between these carbon again. And we could just add on H's to make each carbon has a total of 4 single bonds, right? So we're going to put on H's there. Now, the general formula again, we say CnH2n. And so if you notice this, if we have 4 C's, we must have 10 H's because 4 times 2, that's why you have this 2 right here. 4 times 2 is 8 plus 2 more is 10. So if C is 4, H has to be what? 10. All right. We're just getting the meat of the matter now. So those are just simple, basic examples. Now, how to name alkanes is that you put on a prefix. The prefix which would be part of the name, and then you're going to have a suffix to it, and you get the total name. So a prefix, suffix, and the total name. Now, the prefix is based upon the number of carbons, right? And so, for example, if you have 1 carbon is meth, if you have 2 carbon is eth, if you have 3 carbon is prop, if you have 4 carbon is bute, if you have 5 carbon is pent, if you have 6 carbon is x, like a hexagon, 7 carbon is ept, and then 8 carbon is oct, 9 carbon is non, and 10 carbon is dec. And you need to know the number of carbons as related to the prefix of the name. The suffix now for all alkanes add ane. So the names of the first 10 alkanes will be methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. First 10. All right? So please just make a note of that. Now, we're going to jump into examples real quick. All right? Again, the general formula to remind you before getting the examples is CnH2n plus 2. All right? And so if the carbon is 5, then therefore going to be 2 times 5 plus 2, that's going to be 12, yeah? All right? And that's pentane. 5 carbon is pentane. That's a formula for pentane. All right, so now, just show you all the examples now. Again, I'm going to make this kind of go fast, so just bear that in mind. So if we have methane, methane only has 1 carbon, so 2 times 1 is 2 plus 2 is 4. All right, and notice there, you just choose anyone and work the formula, get it right. So those are the first 10 formulas for all alkanes with their names as well. All right, so example of structural formulas of alkane, just to show you real quick. And from this, you need to know isomers as well, just to make mention of that. All right, remember that we have our 4 lines or 4 single bonds around a carbon atom. All right, so methane, for example, is only 1 carbon, so therefore we have 4 single bonds, which means 4 H is going to add because hydrocarbons are only carbon and hydrogen. All right, I'm trying to race against time. All right, so that's formula CH4, just to go back. So methane is CH4, as we know by now. Ethane, for example, is another one there, single bond between the 2 carbons. Then we put on 3 on each, so a total of 6 H's we can add to that. All right, so that's going to be CH3. So notice you have CH3 first, attached to another CH3, and you can forget the single bond in between, right? You don't need it really. I just put it there for you to see. You can actually drop it out. All right, and so butane, for example, let me just do this one real quick. Whether on the lines on them to make 4 single bonds around each carbon. And then we add H's to all of those extra lines we put on, our extra bonds. And what we have there is CH3, CH2, CH2, and CH3 in that combination. And what you can do is look at the molecular formula by the simple adding all the carbons and all H's together, as we did in the table. All right. All right. So properties of alkanes now, real quick. Properties of alkane. Alkanes are nonpolar. They are insoluble in water. Alkanes are colorless. They are the smaller ones of alkanes, they are normally gases. That means the first 4 members of alkanes, they are gases. So if you remember from methane up to butane, they are gases. All right? All right. They are normally gases. All right? And then the larger ones now are normally liquid into solid. So as they get larger, they become solid and then become also waxy. You notice here we have methane is a gaseous gas. It's kind of funny to say gaseous gas. And if you look at like octane, right, is a liquefied gas, is like petrol. Let me not say gas because it's not. We say all the gas because we use as a common term. It's a gasoline, right? So it's liquefied. So you notice here the first word is gaseous as gaseous, and then as you go down the line, for example, octane, then becomes a liquefied, then become more solid. All right. Alkanes are less reactive than alkenes and alkynes. And the key word you need to know about alkanes, they are saturated. We use them as saturated hydrocarbon. They're full with hydrogen, so they are saturated hydrocarbon, right? All right, let's quickly jump into alkenes and, well, oh Lord, this isomers first, we'll go alkenes. Isomers of this real quick. Now, basic, I'm not going to go through much isomers after this, but this is the last one before going to alkenes. Isomers, you can have a straight chain, and then you can branch off a little bit. It's still butane will be the name. And if you branch off right here, this is going to have a name now. It's isobutene, which is really an isomer of the original butene. And if it's a cyclic form, we're going to call it cyclobutane, right? So notice they are all butane, but their isomers are featured. Different ways to draw the same thing. So isomers now, they have the same molecular formula, but different structural formula. The structure is different, but they add up all the C's and all the H's, they are exactly the same. The molecular formula is the same. That isomers. Please know how to draw isomers, okay? Please. All right, alkenes now. Similar concept, but just the formula is different. The formula is CnH2n. All right, and so quickly, let me just run through that. So again, the unique thing about alkenes form double bond. All right, at least a double bond between the carbon. It must have a double bond. So alkenes, ANE, single bond. Alkenes, double bond. General formula, CnH2n. CnH2n. N is the number of carbon atoms as we talked about it before. All right, so again, for example, we put a double bond here. So if we work out the number of carbons, but first let's put our extra elements on, which is hydrogen in this case. All right, again, we put 2 on this one. This one can only hold 3 because we have, can only hold 1 more because we have 3 already. All right, and of course, if you count the number of carbons and H's, you realize that we get 4 C's and 8 H's. All right. All right, let's go down a little bit more now. All right, so naming the simple alkenes, the prefix again, suffix, name, same concept. The only difference here, we're going to add ene, okay? That's the only difference. So again, point to note though, the simplest member of the alkene group is not methane because there's not such thing as methane, right? It started F. So, because it must have a double bond. You can't have a double bond between a carbon by itself, right? So you must have 2 carbons at least to form a double bond. So therefore, the simplest member of the alkene group is ethane, 2 carbons. All right? And so again, we had ene at the end. Alkane is ane. The naming now does say, okay, ethene, propene, butene, and so on. All right? And to decene. Those are the first 10. Once you know the first 10, you're straight. All right. Now, again, just remind of the general formula. And just look at quick examples right there. For example, if you have 5 carbon, if C is 5, then you're going to have 2 times 5 is 10. So you're going to be H10 quickly. All right. And that is pentene, for example. All right. So this again is the prefix and name and formula that we're going to have for them. So again, based on the number of carbons, if it's 2 carbons, it's twice the number. So for alkenes, notice that the C and the H's are twice the amount of carbon. All right, that's the bottom line. Simple stuff. Now, again, we must have 2 lines. We must have 2 lines between, which we call them double bonds, between at least 2 carbons. And so what you have here now, again, just put on 2 more lines on. All right, and here, for example, ethene. You may call it ethene for some of you. Depends on how you pronounce these things. All right, ethene, same thing, right? All right, so here we put on our 2 extra because we already have a double bond there and put on our H's there. That's the structural formula for ethene. All right, and notice we have CH2. Again, the molecular formula will be C2H4. All right. Propene, just look at it real quick as I just quickly going through this. Just look how I'm adding the H's on. All right, and that will be the condensed. I didn't mention that earlier, but what I draw at the bottom, those are the condensed structural formula. So the structural formula is a whole thing, the expanded version. But when you reduce it, we call it the condensed structural formula. I forget to mention that, right? I'll try to really finish this in time, man. Time is going. All right, so butene is the next example right there. Again, just look how the H's will be on. All right, no need to hang up on that. All right. The properties of alkenes now is that they are non-polar just like alkanes. All right, they're insoluble in water just like alkanes. The similar ones are also gases just like alkanes. The larger ones will form liquid, just like alkanes. So the properties are pretty much similar. The more reactive than alkanes, however, all right, they're unsaturated, and unsaturated, once you have a double bond or triple bond, is unsaturated. Now, the next structure we're going to go on to after this is the alkyne. So similar here is isomers again. The similar way, I don't need to even hang up on that too much, is also draw them, redraw the structure. You get isomers. They're isomers of butane. Alkynes now. Pretty much, a matter of fact, I think I could even skip over this. But let me just do it real quick. Alkynes now, they now form triple bond. So alkane is single, alkene double, alkynes are triple. All right? Because I still have something else to do after this and I finish. So here now, the general formula for alkynes will be CnH2n minus 2. All right? So minus 2 in this case. So there must be a triple bond. So notice I put on the H's. They put a number of lines to make each carbon has 4 single bonds in total. All right, and so notice here, based on the general formula, it works out to be, we have C4H6. So if you multiply 4 by 2, you get 8, minus 2, you get 6, all right? So therefore, it is C4H6 for this compound. Could you guess what the compound is this by number of carbons, by the way? Could you guess? It's 4 carbons, you could guess it, right? All right. Now let's name them real quick. Prefix again, suffix, name. All right, the prefix, suffix, name, prefix, again, because it's alkyne, you must have a triple bond. You don't have triple bond between only a single carbon. So you must start, the simplest one is eth. All right, and so it goes down into ethene, I should say, not ethene, ethine, we're an alkyne, all the way to decyne. Again, the suffix will be yne, all right, and then so the names will be ethine, the simplest one, all the way to decyne. All right. Now, some examples really. Let's say carbon is 5. Then, of course, you just multiply by 2 minus 2. So it's 10 minus 2 is 8. All right? And that is pentyne. 5 is pent. Remember, so it's called pentyne in this case. All right? Now, formulas again. Just work out the formulas. I'm gonna hang up on this thing real quick. If you have two C's, then going to be so notice here, if you have 2 C's, it'll be 2 times 2 minus 2, get back 2, all right, and so on. So if you notice as you go along, that's where you're going to get them right here. 6 minus 2 is 4, so C3H4, and so on, all right? So just notice the numbers as you go along and work out the formulas. You can practice those if you do not understand them fully, all right? All right, sorry I can't explain everything. Very, very sorry. Just moving with time now. All right, so let's just pass this slide. All right, let's talk about ethine, for example. We already have a triple bond, so we only need one more bond for each carbon to make it 4 total bonds. All right, so we have one of our H's there. All right, and so we have CH with a triple bond. All right, so we have 2 C's and 2 H's. All right, for this is propyne. Again, just put on the bonds, put on the H's, condense the formula, and you get that. All right, so again, butane that we did earlier, that I was asking about if you can guess the name, this is butane right there. All right, properties of alkyne. Alkyne are also nonpolar, just like alkenes and alkynes. Alkanes and alkenes. So alkynes are the same in terms of not being nonpolar as alkanes and alkenes. Insoluble in water, just the same. Smaller ones are gases. And notice once you reach the 4th carbon, those are the gases for all of them. Up to member number 4, they are gases. After that, they become liquefied a little bit, and they become a little bit more solid as they go along and waxy. All right. Generally, alkynes are more reactive than alkenes and alkanes. Just to make mention of that, we have saturated. They are unsaturated because double bond and triple bond, they are unsaturated. Alkanes, they are the only saturated ones. Just to make mention of that. And so you need to know different reactions as well of these things: reactions of alkanes, reactions of alkenes, reaction of alkanes, alkynes. So for alkanes normally go through substitution reaction, right? Generally, that's what alkanes normally go through. But for alkynes and alkenes, they will go through like addition reaction, they will go through like halogenations and so on, right? So you need to know those things. However, as I mentioned, that alkanes are normally substitution reaction because alkanes, and I hope I said it right because in my mind I think I said something wrong. I don't even remember what I said. But alkanes, just to clarify, alkanes will undergo substitution reaction because one of the H must be replaced by something else. All right, so that's the mention of that. But alkenes and alkynes, they can go through addition and so on. All right, addition reaction, halogenation, and all of those reactions. Right. All right. So again, as isomers, again, just a similar concept, just to form different shapes with them as best as possible. And you do have to have a cyclic one in your isomers. You can have different types of thing in the isomers. So you can just make them branchy all over the place. Branch, two branch, one branch, and all of that. So practice writing isomers, okay? All right, esterification, now we're going to finish up. Esters are normally have a fruity aroma, nice sweet smelling compounds. They are organic compounds, so we call them aromatic organic compounds. So esterification is the production of ester by reacting carboxylic acid. You need to know your carboxylic acid homologous series as well. You didn't know that. With an alcohol, you need to know your alcohol homologous series. I didn't been through those, but please make sure you go through alcohol and carboxylic acid if you want to understand your organic chemistry, all right, and the different reactions. So once you react the acid with the alcohol, you get ester, all right. And so to make this happen, though, you need an acidic catalyst and also some form of energy, which is heat generally, to make this work, all right. So the functional group for carboxylic, the carboxyl group is in carboxylic acid. It is a COOH, or you may have C double bond OOH, and for hydroxyl, that is in alcohol. All alcohol will have OH, which is the hydroxyl group. All right, so when you put them together like that now, when you put both the carboxyl group, notice the H from the carboxyl group, when you remove that and add on something to it, it becomes an ester. So that's how an ester will look. That's the ester group. So if you see a C double bond OO and like a dash, it means an ester group. All right, so that's an ester homologous series. So again, organic acid plus alcohol give you ester and water. All right, just to make mention of that. Again, once we join them like that, the H and the O, so the H from the acid with the OH from the alcohol come together to form water, and so you have here the ester compound or functional group for ester. All right, so water is a product. And the R's represent, let's go back one little bit. The R's represent our side chains, our carbon chains, right? So those are our side chains or our carbon chains. So a typical example here, if we're going to react ethanoic acid with methanol, all right, what's going to happen here, and I just want to point this out quickly, the water will be removed, and then the methyl, I should say, from the alcohol will join to the ethanoic. But there's a name how you name this now. You name the alcohol part first, like the methyl, which is coming from methanol, is named first, and then you will name now the acidic part last, which is ethanoic acid, becomes ethanoate. So this compound is called methyl from the alcohol, and ethanoate from the ethanoic acid. So that's how you name esters, all right? All right, and of course, what is the product? All right, so propanoic acid with ethanol. Of course, again, you're going to get ethyl, you get it ethyl and propanoate. So again, the water removes, put that in. Notice that piece in red, form a side carbon chain. So this is going to become now ethyl propanoate. All right. So this is really almost, this is, I think, the last slide. Yeah, I think we're going to stop here for tonight for sure. All right, so again, use of ester. And this is for you just to just browse through really to pick up a few things, right? So don't stress yourself too much if you don't understand everything. All right, so use in fragrance and also in soaps and detergents. Use in perfumes as a function or use of ester. Used as flavorings as well, sweet smelling. Using food colorings and so on. Used in medicines. Used as solvent in glues. All right, so those are some of the basic uses for esters. All right, thank you for being here. It's been a long journey. I know you're anxious to go get some rest for exam, but good luck. No time, not wasting any more time. Talk to you soon. All right, hope you do well. Please get some rest before the examination. Talk to you.